Today I'm going to be going over different characteristics that you might see on a graph. So we're going to be going over how to determine if an equation has a hole, a vertical asymptote, or a horizontal asymptote. Okay, so the first one is a hole. So first, let me show you what a hole looks like on a graph. So here is my XY axis, and then I'm going to quickly draw a function that has a hole. So in this case, I have a function that's defined everywhere except this hole right here. So let's look at an example of an equation that would have a hole. So if I have f of x is equal to x plus 2 over x squared minus 4, I want to determine if this rational equation has a hole. So the first thing that I'm going to do is factor the denominator. Okay. X squared minus 4 is a difference of squares, so it factors to x plus 2 times x minus 2. Now, we run into a bit of a problem, because if I plug in negative 2 to this equation, so if I did f of negative 2, I would get negative 2 plus 2 over negative 2 plus 2 times negative 2 minus 2. Negative 2 plus 2 is 0. Negative 2 plus 2 is 0 times anything, so it doesn't even matter what this is 0. We have a problem here. This is what we call an indeterminate form. So our function is not defined when x equals negative 2. However, if you look up here, I have x plus 2 as a factor in my denominator. So actually, these guys would divide into 1. So I'm going to back up a little bit. So if I simplified this, I'd end up with f of x equals 1 over x minus 2. Now, we can't pretend that this didn't exist, because this is our original equation, and it's still true that negative 2 leaves us with an indeterminate form. But this equation right here is equivalent to it, but it no longer has the issue that if I plug in negative 2, I get an indeterminate form. So what we say about this graph, f of x equals x plus 2 over x squared minus 4, is that we have a hole at x equals negative 2. Now, what I like to use the phrase is it's a hole in one. So essentially, if you have a factor in the numerator and that same factor in the denominator and they divide out, that is where you're going to have a hole. Note that the entire denominator does need to be factored. You would have to factor out the exact same factor that's in the numerator to make it work, and make your cancellation so that it's possible. So that's it for a hole. The next thing we're going to review is a vertical asymptote. Okay, so the next characteristic of our graph that we're going to look at is a vertical asymptote. So as you can see, I have 4 sets of axes drawn here. That is because there are 4 different cases we could potentially have going on for our vertical asymptotes. So we could have actually 2 different kinds of vertical asymptotes. We could have what we call even vertical asymptotes, or we could have odd vertical asymptotes. Okay. Then what we need to do is actually draw where our vertical asymptote might be. So a vertical asymptote is any x value that when your function moves towards, it goes off to either positive infinity or negative infinity. Another way to phrase it is as your function approaches that x value, it becomes unbounded. Okay, so our even vertical asymptotes, as our functions are cruising along from the left side and the right side, they either both go to positive infinity or they both go to negative infinity. Okay. Now, if we have odd vertical asymptotes, it's the opposite. So from one side, your function is going to be unbounded up to positive infinity, and from the other side, it's going to be unbounded down to negative infinity. So let me draw in my vertical asymptotes here. Okay, so on one side, we're going to go all the way up to positive infinity. The other side, we're going to go down to negative infinity. And then I'll make it opposite here so you can see all of our cases. Okay, so one goes to positive infinity. I don't know why I wrote it like that. So one of these is going to positive infinity, the other is going to negative infinity. Can't write it quite as cleanly as those ones, but you get the point. So now, how do I find if my graph has vertical asymptotes? Well, here is what you do. We're going to go through an example. I'm actually going to use the example from when I demonstrated how to find a hole. So our example was f of x equals x plus 2 over x squared minus 4. Okay, so we already determined that this actually had a hole, but it also has a vertical asymptote, and I'll show you how I know that. So your first step for any problem like this where you need to find vertical asymptotes is determine if there are any holes. So step 1, determine if the function has holes. Because if it's a hole, then it's not going to be a vertical asymptote, and you need to remove that hole so that way you can determine where the vertical asymptotes are. So if you remember from the last segment that I just did, we factored our denominator, and we determined that we have a hole at x equals negative 2. That was the value that if I plugged it in, I would get 0 over 0 form. Okay, so this, we have a hole at x equals negative 2. Now, in order to find our vertical asymptote, I want to, let me put this in parentheses, I want to use the simplified version of this so that I don't mistake any holes for potential vertical asymptotes. So I'm going to now use this equation. Okay, now to find if we have vertical asymptotes, step 2 is set the denominator equal to 0, and solve. Okay? So now, I'm going to take x minus 2 and set it equal to 0. I'm going to add 2 to both sides. So I have a vertical asymptote at x equals 2. I'm going to put VA at x equals 2. So I was able to determine. Now, is it even or odd? So here's how you determine that. X minus 2 is really x minus 2 to the first power. That is an odd number. So therefore, it is going to be an odd vertical asymptote at x equals 2. So specifically, it's going to be an odd vertical asymptote at x equals 2. If it were instead x minus 2 squared, then it would be an even asymptote, and they'd either both go up to positive infinity or both go down to negative infinity. Okay, so up next we are going to determine or learn how to determine if a graph has any horizontal asymptotes. So the last characteristic that we are going to cover are horizontal asymptotes. So first, let me just show you what a horizontal asymptote looks like on a graph. So you could have something like this. Okay, and our horizontal asymptote would be right here. Okay, so what is happening here? Basically, all a horizontal asymptote is if you have a function, and as the values get really, really large, okay, go off to positive infinity, then those values start getting really, really close to a particular number. So in this case, for this function, as our x gets really, really big, in other words, goes off to positive infinity, we are getting very, very close to 0. So here, we'd have a horizontal asymptote of 0. Now, same idea over here. As x gets really, really, I guess, small, but as x goes off to negative infinity, our values are getting really, really close to 0. So this would be an example of a function that has a horizontal asymptote at 0. Now, one thing my students kind of get a little caught up in is a lot of us like to say, well, it's a line that our function will just never cross. Okay, that's not necessarily true, because what if instead the middle of my function looked something like this? Oops. Okay, but still, even though we've crossed where this horizontal asymptote is, the endpoints of my function, as I'm going all the way off to positive and negative infinity, we're still converging to 0. So a horizontal asymptote is not an invisible line that our function can never cross. It's simply what is happening with the end behavior of your function. So as we go to positive infinity and negative infinity, is there a value that your function is getting really, really, really close to? Okay, so now that we've covered that, we need to cover how to actually find if your function has a horizontal asymptote. So to do this, there are 3 different cases. Case 1. Okay, so if you notice up here, I said that we're going to define f of x as this rational function here. A rational function is just a function that has a polynomial in the numerator and a polynomial in the denominator, okay? So case number 1 is that q of x up here, so the degree of q of x, okay, is less than the degree of r of x. Another way you can say this is that the degree of the numerator is less than the degree of the denominator. Well, if that's the case, then we have a horizontal asymptote at y equals 0. Okay, our second case is if the degree of the numerator is equivalent to the degree of the denominator. Then we have a horizontal asymptote at y equals a over b, where a is the leading coefficient of q of x, okay, and b is the leading coefficient of r of x. Okay, and if you need a little refresher on some of these terms that I'm using, like leading coefficient and degree and polynomial and all that stuff, I'm going to link a past video here so that you can go and refresh your memory a little bit on those. Okay, so case 3 is when the degree of q of x is greater than the degree of r of x. Okay, well in this case right here, I'm gonna case 3, there is no horizontal asymptote. Actually, there is what we call a slant asymptote. And you can find the equation of the slant asymptote by dividing the numerator by the denominator. So this is no horizontal asymptote, but there is a slant asymptote. Okay, so now what we're going to do is go through an example and determine if an equation has a horizontal asymptote. I'm going to do 2 different examples that demonstrate case 1 and case 2. In this video, I'm not going to worry about case 3 just because I could pretty much do a whole nother video on finding slant asymptotes and doing polynomial long division. Alright, so here I have 2 examples for you all. The first example is f of x equals x to the 5th minus 3x all over x to the 8th minus x to the 7th plus 1. So the way we determine if we have a horizontal asymptote is we need to know the degree of the numerator and the degree of the denominator. The degree of the numerator is 5 and the degree of the denominator is 8. Remember, it's the highest degree in a polynomial. So in this case, the degree of the numerator is greater than the degree of the denominator. Okay, so that means, based on our rules, that we have f of x, this f of x, has a horizontal asymptote at y equals 0. Okay, so now, number 2, we have f of x equals 6x cubed minus 1 all over negative 2x cubed plus x squared minus 1. So, in this case, the degree of the numerator is actually equal to the degree of the denominator. So the degree of the numerator is 3, and so is the degree of the denominator. Okay, and so that means that we have a horizontal asymptote at y equals. Now, the way we determine the horizontal asymptote is we take basically a ratio of the two leading coefficients. So those are the coefficients that are attached to the variable with the highest degree. So it's going to be 6 over -2, which actually equals -3. So we have a horizontal asymptote at y equals -3 in that case. Okay, that's it for this video, and